Good morning, students. Let us start the class. Today there is rain in Bengaluru, and on the way also I was stuck up in rain, so I could not reach college on time. That is why today's lab class is delayed. Anyway, I still waited for some more students to join. Now let us start the class. In the previous lab, we had seen the common source amplifiers, simulation. Today, let us see how to make a layout of the common source amplifier. Later on, let us proceed with the common drain amplifier. So, let me just show you the circuit diagram of the common source amplifier once again for you to revise. This is the circuit diagram of the common source amplifier, where, let me zoom in. Yeah, now you can see the complete circuit. Now here you can see that we had used, instead of 180 nanometer, we had used 1 micrometer, and width we had increased. 20 micrometer is the width of N MOSFET, and 50 micrometer was the width of P MOSFET. Now, in all our earlier layout experiments, it was quite easy for us because the devices were quite smaller. Now, the device is quite bigger because it is in the micrometer size. So, please remember these connections: body connection of P MOSFET, body connection of N MOSFET, and drain to drain short, which is output, and the gate of PMOS is connected to V bias, and the gate of NMOS is connected to input signal, along with VDD and VSS connections. You'll have to remember this because I'll show you now the layout. So here you can see that the channel length of this device is 1 micrometer, whereas the width of the polysilicon remained earlier, it is 180 nanometer. You don't have to worry about this compression. This compression has happened because of the screenshots compression. It is not actually there on the screen as such, but because I am using the lab manual, in the lab manual, the image was somewhat cropped that way. That is why it is shown like this. Otherwise, all these are squares. Now, the input to the N MOSFET, below one is the N MOSFET, input to the N MOSFET is V in. So you can see the metal to poly via here with the yellow color contact area or contact cut, and the blue color metal area, and the overlapping larger area is polysilicon area. Even to the P MOSFET, which is at the top, the gate is connected to the V bias. So this is V bias, and you can see the drain and drain of NMOS and PMOS are connected, and you can see one pin here, that is the output pin. Now you can see upper one P MOSFET is surrounded by a orange line. That orange line is basically N well, and the N MOSFET is on the dark screen itself, and that is P substrate. Now let us see how to make the other connections. Now you can see here, let me zoom further. You can see this PMOS is such a big device now. Its channel length is 1 micrometer, but its width is now 50 micrometer. So you can see so many contact cuts adjacent. Now left side is the source terminal, right side is the drain terminal, and you can see so many contact cuts there, yellow colored ones. In the middle it is the polysilicon or the gate area. Now left side is the source area, right side is the drain area. That is how we have taken it. Now we have to connect one VDD at the top, and the source of P MOSFET should be connected to VDD. Now the body of the P MOSFET is this orange colored N well. N well also needs to be connected to VDD. So what is done here is you can see a via here. It is a metal to N-well via, N-well to M1 via. So top side metal is connected to VDD. At the bottom there is N-well. N-well is connected to the N-well there. You can see the overlap there. But now you can see there is a scale at the left side. When you start working with the cadence tool, if you press Shift K, the scale will appear on the screen. And the scale will show the dimensions in micrometers. Now you can see at the top it is 0, at the bottom it is 5. Means the total dimension is around 5 micrometer here. The device is still bigger. Now you can see at the 10th micrometer, one more via is there. Now this is the necessity of the design, that every 10 micrometer we should connect the body of the P MOSFET to VDD, because the device is now very big. Only one connection is not sufficient. As you can see, there are so many yellow color contact cuts everywhere. It is to have an effective connection between the implant area and the metal. Metal is at the top, implant is at the bottom. So you can see so many yellow colored contact cuts. Similarly, this is a DRC rule, design rule check. There's a design rule that every 10 micrometer, the body of the device must be connected. If it is P MOSFET, it should be connected to VDD. If it is N MOSFET, it should be connected to VSS. Otherwise, as the body is much larger, there can be induction of leakage currents anywhere. Leakage charges can be there anywhere in the body. So this is a design rule. For every 10 micrometer, we should connect a via. That is why a scale is required here now. And you can see at the 10th micrometer, one via is connected. And this procedure should be repeated for every 10 micrometer as such. Now this is the connection. Let me proceed now. Similarly, for N MOSFET, you can see even N MOSFET is quite larger. It is 20 micrometer wide. You can see there is a scale here. And the source of the N MOSFET is connected to VSS. You can see a via here. Let me zoom in. You can see a via here, where this via is nothing but M1 to P sub, because the P substrate itself is the body of the N MOSFET. So it is connected there, and we can see every 10 micrometer, one more connection is made here. Every 10th micrometer, there is a via connection, body to VSS. So this way, we have to place the vias. And finally, now we can see the layout. Let me zoom in further. Yeah. Don't worry about that square now. That square is basically because I have enlarged the image. It is showing as a square. Here, each pixel is basically a square. But we are dealing with micrometer and nanometer dimensions. You need not worry about the squares there. So now, this is the N MOSFET. Whatever is the cross you are seeing, that is basically the grid point in the cadence tool itself. Now at the top we have VDD, and the body of the P MOSFET is connected to VDD, and you can see all these metal lines. In between it is polysilicon, the gate area. Every 10 micrometer, there is this VDD connection of the source. See, it is such a lengthy device, such a big device. Now at the input we have this via. Actually the via is not shown here. That via is still there. And again, drain are connected, and the drain connection itself is output, and the source is connected to VSS, and even the P substrate is connected by means of a wire to VSS. And every 10 micrometer, we have that VSS connection. At the bottom, we have the VSS path. Now, this is the common source amplifiers layout. As I have been telling you earlier also, layout is basically a art or basically a personal style. In this common source amplifier, we have made the layout in the vertical fashion. That means we have placed the devices in the vertical way. It is not mandatory that devices have to be vertical always. They can be horizontal also. In the next experiment, I will show you, we have made it purposefully horizontal. so that there can be multiple ways of making a layout. Ultimately, layout is a personal style or it's an art. Our idea is that DRC check, LVS check, RCX check should happen, and the layout must be ready to be fabricated with all the design rules met, and with the area as minimum as possible, performance as maximum as possible. That is the idea. Now with this, now I have finished common source amplifier. Let us discuss common drain amplifier now. So today's experiment, after the common, you can see now the common source amplifier is completely out. The top one is P MOSFET, the bottom one is N MOSFET. You can see the P MOSFET is totally 50 micron in width, where for every 10 micron, one via is kept. There are totally 6 vias now. In N MOSFET, as it is only 20 micron, every 10 micron, one via has to be kept. One at the top, one at the bottom, one at the middle. So you can see 3 vias there. In the case of P MOSFET, you can see 6 vias there. So this is the common source amplifier, complete layout in the vertical fashion. Let us proceed to common drain amplifier. But before that, let me stop sharing this screen and let me write something else on the screen. Okay, let me write the common source amplifier here. So this was Vi and this was V0 or VO. So the lower transistor was the amplifier transistor, the upper transistor was working like a resistor. Resistor was replaced with the P MOSFET here. So now input is given to the gate, output is taken at the drain, and the source is common in case of the amplifier transistor. Now this is common source amplifier, which is analogous to common emitter amplifier when you worked with BJT. Now let us try to rig up the common drain amplifier, which is analogous to the common collector amplifier with BJT. Common collector amplifier means it is emitter follower. You have to recall learning of that emitter follower. It's unity gain amplifier. It can be used as a buffer amplifier, means it can provide current gain. Input impedance is high, very high there. Output impedance is very low there in the case of a emitter follower. Now, even using MOSFETs, we can have a common drain amplifier where I will just write the emitter follower circuit first using the BJT. Now this was emitter follower circuit with BJT. This was input, this was output. Output was taken at the emitter. Collector being at AC ground, it is common to base and emitter. So it is called as common collector configuration. And as output is unity gain and there is no phase shift. If input is like this, output is also like this, there is no phase shift. So output at the emitter follows the input at the base. That is what is called as emitter follower. And its input impedance is very high. That is its basic advantage, and it can be used as a current gain amplifier. Now in the MOSFET, if we have to implement it, as we had a NPN type BJT here, we can replace again the same thing with the N MOSFET. Now N MOSFET we connect it to VDD, and this is now V in. And then we take output here. This is V0. And this resistor we have to replace with one more device here now. Because as I have told you, resistor is quite expensive inside the chip. Resistor consumes a much larger area. Now you people have to give me the idea about how to replace the resistor now at the bottom. Should we use P MOSFET? Should we use N MOSFET? How can we have a resistor implemented using a MOSFET? You people have to give me the idea. Later on, I will write it.
Sir, are you drawing on the screen?
Yeah, I am drawing on the screen.
Because we can't see what you're drawing.
No one is able to see. I have shared this.
I'm not able to see.
What about others? Yeah, others are able to see. So, Vanilla, you can leave the meeting and join again. You may be able to see. So, anybody can give me an idea about how do I write a resistor?
Excuse.
Yeah. It is better that you leave the meeting and join once again and refresh. Either refresh it because I have shared
Yes,
this.
sir, now it is visible.
Yeah, yeah. Okay, let me explain this once again for the students who could not see the screen earlier. At the leftmost part of the screen, I have written the common source amplifier. Now this is common source amplifier, where we had used one N MOSFET as the amplifier transistor and P MOSFET as the resistor. Now, in the middle I am writing a emitter follower, or this is now a common collector amplifier using a BJT. You can see the collector is the AC ground because it is connected to power supply. Input we are giving it the gate and output we are taking it the emitter. So input we are getting the base. So there is no phase shift here and the gain is almost unity. That is why it is called as emitter follower. And at the bottom we have this RE. We have a resistance at the emitter across which we are taking the output. And here we had RB in the case of BJT. That was a biasing resistor for BJT. Now, as MOSFET does not require any biasing resistors, we are directly giving the input to the gate of the N MOSFET at the top. NPN I have replaced with N MOSFET now. This is that. NPN I have replaced with N MOSFET. Now I want students to give me an idea about how to implement a resistor here, so that I can replace this resistor by means of a MOSFET. But should I use N MOSFET or should I use P MOSFET is the question. Students have to give me an idea.
So we'll use NMOS only.
Okay. Okay. Kuldeep has also told the answer, NMOS with the pull down network. So let me write NMOS here now. And let me connect it to VSS now. I have connected N MOSFET, I have connected to VSS. Now this can be that V bias. I should write it in capitals because it is DC. This is V bias, just like we had V bias here earlier. Now we are using NMOS here because NMOS passes good 0, PMOS passes good 1. If at all we write PMOS, it is possible to implement resistor using PMOS also. But if at all we write PMOS, how do we write PMOS? Let me clear all this, or let me clear it completely. Now let me write it again. So we give a signal here, we take out the signal here. Now this is that V bias. So the lower NMOS can be used as a resistor, and you can see input is given at the gate, output is taken at the source, drain is connected to VDD, now drain is AC ground, so now this is a common drain amplifier. This is now a common drain amplifier, which will have a high input impedance, higher bandwidth, low output impedance, and it will have a current gain. Only problem is it does not have a voltage gain. It's a unity gain amplifier. So in practice, whenever we have any electronic systems, we will not have a single amplifier anywhere. We will always have multi-stage amplifiers. In the beginning, we will have a pre-amplifier, and in the middle, we will have some medium gain amplifier. At the end, we will have a power amplifier. Because in a single amplifier, all the ideal characteristics are not achievable. That's why we have different configurations. Common source amplifier can be used as a pre-amplifier in the beginning, and common drain amplifier can be used as a impedance matching amplifier also, because it has high input impedance, low output impedance, and it can be connected to a power amplifier later on. And this common drain amplifier is going to provide us with the current gain also. So always in practice, we will have multi-stage amplifiers in our electronic equipments or in electronic applications. Now my next question is, if at all we replace it with the P MOSFET, how it should be? Let us say I want to replace it with P MOSFET. How it should be? Let the amplifier transistor at the top remain as NMOS. And I have not yet written which side is source, which side is drain. Now let this be V bias. How should I write P MOSFET now? Naturally, in case of P MOSFET, source is at the top, drain is at the bottom. Because in the case of N MOSFET, current is flowing out of the source. In the case of P MOSFET, current is going into the source. So source should be at the top, drain should be at the bottom. This way also we can connect. But the point here is P MOSFET passes good 1. So it is suitable that PMOS is always connected at the top, NMOS is connected at the bottom. But in this case, as we are using it as a resistor, we can use P MOSFET in this way also, because if you want to have a resistance, we can have it. So this is another option of having a P MOSFET as a resistor. Now my next question is, if at all we want to use PMOS only as a common drain amplifier, can we connect it? Instead of N MOSFET, let us say we want only P MOSFET. It is as if it is analogous to, instead of using NPN transistor BJT for emitter follower, we can use PMOS also as emitter follower. But the connections are in a reverse way. Similarly, it is not necessary that common source amplifier has to be always having PMOS at the top for resistor and NMOS at the bottom as an amplifier transistor. We can use the other way also. Only thing is, in the case of NPN, it is easy to work with it because it is all having positive voltages. Same case with the NMOS. In the case of NMOS, it is easy to work with because we all have positive voltages. In the case of PMOS, we should always have negative voltages. That is one point. Second point is mobility of the NPN is better than PNP as far as the charge carriers are concerned. Similarly, the mobility of electrons is larger, mobility of holes is lesser. So it is always better to use NMOS itself. So that is the reason we are going for NMOS now. Now in this case of NMOS, you can see. Now if you compare both of them, if both can work as a common drain amplifier, which one is having more advantage? Can anybody tell me? Both are now common drain amplifiers only. Only the resistor is replaced with a different device. Now, which one is more advantageous? The left side one or right side one? You have to tell me. Kuldeep says it is left side one. Why? Why? Any answer? In right side, we need to create N well. Exactly so. Right. In the left side, you are having two similar devices, NMOS and NMOS. But at the right side, P MOSFET has to be in N well and NMOS is on P substrate. So we will have one more process of fabricating N well. But in the earlier case, we went for PMOS at the top and NMOS at the bottom. There we had to do it. Why? Because PMOS was connected at the top as a resistor. There also we could use NMOS as a resistor. But again, as I told you again and again, NMOS passes good 0, PMOS passes good 1. It is always better that PMOS is at the top. That's why we had gone there. But here we have no such necessity. We don't have to use PMOS at all. We can directly use two NMOSFETs only on a single P substrate. That is the advantage. So left side circuit itself is the better circuit. So let me stop annotating this. Let me stop sharing this. And let me start sharing the lab manual again. Right. I hope you can see the screen now. I have shared the lab manual again. Today's experiment is common drain amplifier. The procedures remain similar to the previous experiment. Enter the schematic diagram with the upper NMOS device dimensions as length equals 1 micron, width equals 50 microns, and the lower NMOS device dimensions as length equals 1 micron, width equals 10 microns. In today's case, the upper device is the amplifier transistor and its width we are keeping purposefully high, and the lower device's width is 10 micron because we are using it as a resistor now. In the earlier experiment, we had purposely increased the width of the P MOSFET as such. We had kept the N MOSFET width as 20 micron, P MOSFET as 50 micron. There, it was the mobility issue of the charge carriers. Today's experiment, both are same type of MOSFETs. But the lower one is working like a resistor now. So it can have a lesser width as such. So that is why we keep it as 1:50 for the amplifier transistor and 1:10 for the resistive transistor. All other things are same. Let me zoom in so that you can see the circuit. You can see the circuit now. In the previous experiment, we had kept the VDD symbol here and VSS symbol here. That was one style. Now there can be one more style. Instead of VDD and VSS symbol, you can connect a pin here and one more pin here also. Now, when you make a symbol also, when you make a symbol for this amplifier, even the symbol will have these pins To the pins directly, power supply also can be connected. That is one more style. There can be multiple styles of implementing the same circuit diagram. Now here we have shown you the other style where we are connecting two pins for instead of VDD and VSS symbols, and otherwise it is input at the top, V bias at the bottom, and V out at the source of the amplifier transistor. Now this is the circuit. But here you can see the upper N MOSFET's body and the lower N MOSFET's body both are connected to VSS only because it is N MOSFET now. N MOSFET is under P substrate. Actually, N MOSFET is above P substrate. It is fabricated on P substrate. So P substrate has to be connected to VSS. That is what is this connection here now. You can see 1:10 for the lower transistor, 1:50 for the upper transistor. This is the common drain amplifier's circuit diagram. Now, simulation can be performed for the same circuit. There can be V bias and VDD and V out pins. That is what is shown here. Then a symbol can be created. Either the default symbol can also be used. Here the default symbol itself is used because the tool itself gives a default symbol as a square, general square rectangle. You can see V bias and V in are input pins. VDD, VSS are there as supply and power supply positive and negative pins, and V out is also present here. Now this symbol can be directly connected, and the V bias for the common drain amplifier is now minus 1.8 volts. Now you can see here this is the common drain amplifier circuit, where at the top you can see power supply is directly connected, unlike our earlier approach where we used to use symbols. As I told you, that is one approach, this is one approach, both are going to yield the same result. So here 2.5 volts VDD is connected, minus 2.5 volts VSS is connected, and input is connected, input AC for the upper transistor, even though it is shown here at the lower side. And for the lower transistor, V bias is connected, which is minus 1.8 volts. And output is now connected to V out pin. Now to the N MOSFET, at the gate AC is minus 1.8 volts. So what is VGSN now? Now as per this circuit connection, to the gate of N MOSFET, minus 1.8 volts is connected. So what is VGSN of the lower transistor? Someone has to tell me. Because the upper transistor is anyhow used as an amplifier. Lower transistor is used as a resistor. What is VGSN of the lower transistor? You will have to visualize the circuit diagram. Kuldeep says it is minus 3.4. I will write it here. And I will ask you to check once again. Because for N MOSFET, VGS has to be positive. Think again. Always for N MOSFET, gate to source voltage has to be positive. Any other answers by any other students? Now Kuldeep says it is 0.6 volts. Let us say now answer given is plus 0.6 volts. I'll tell you, think again. Let me see. Gate is connected minus 1.8 and source is connected to minus 2.5. Minus of minus 2.5 is plus 2.5. So here it is 2.5 minus 1.8. That is 0.7 volts. That's why I told you to think again. VGSN is now 0.7 volts. It is a coincidence that we are getting the BJT's VBE only here. It is just a coincidence. Otherwise, you know that MOSFET MOSFET always have a threshold voltage. Now, the threshold voltage for the N MOSFET has to be positive. For the P MOSFET, it has to be negative. In our earlier experiment, we had seen that the VGSP was basically negative. Now, in this experiment, we are seeing that the VGSN has to be positive because the source of the NMOS is connected to minus 2.5 VSS. So naturally, even though you may think that how can N MOSFET have a negative gate voltage, how it can be minus 1.8. But we are dealing with amplifiers which are having dual supply now, plus and minus both. So when the source is at minus 2.5, gate can be at minus 1.8. Actually, it is between gate and source, it is only plus 0.7 volts. That way, the gate to source voltage of the N MOSFET is positive, and that is when it is working like a resistor there. It will be working in the linear region. That is how these voltages are chosen. Let me proceed. Now, this is the common source amplifiers block diagram, which can be simulated directly, and the simulation output is seen here. You can see the simulation output here, where you can see the phase is 0 degree here. That means the input and output are at the same phase, so you will see 0 degree in the phase response. Now, in the gain response, you will see somewhere around minus 1.4 dB. Actually, the gain is less than unity now. If it is unity, we should get gain also as 0 dB. But it is slightly less than unity, somewhere around 0.98 or 0.97. So in such a case, you will get a gain of around minus 1.4 dB. The lower one is now the gain response. So you have to go all the way down. From minus 1.4, minus 3 dB, you have to go down. Minus 1.4 minus 3 is minus 4.4 dB. So you can see here it is minus 2.2. It is not minus 4.4. You have to go down. You can see the frequency. When frequency increases, the gain is now reducing. Even the phase is also altered. Phase also does not remain 0 degree there. So now, when this is coming down, we should go down further. You can always see that here it is 10 power 9, means 1 gigahertz. You can increase the frequency here to maybe 1 terahertz or 1 petahertz, 1 exahertz. You can keep on going on. 1 yottahertz, 1 zetahertz, 1 yottahertz. You can go on. And you can still try to measure the bandwidth of this common train amplifier. You can see minus 2.2 is here and minus 1.4 here. We have to go to minus 1.4, minus 3 is minus 4.4. Of course, in this screenshot that is not shown, but when you conduct the experiment, when the offline labs start, you can actually observe that if you keep increasing the frequency here, at what point you will get minus 4.4 as the upper cutoff frequency, and that will be the bandwidth of this amplifier. And you can see at the lower side, there is no frequency cutoff for lower frequencies. That is because this is a direct coupled amplifier. We have not connected any capacitors as coupling capacitors here. So it is a direct coupled amplifier. So at the lower frequency, there is no low frequency cutoff. Now, as the next step, after the simulation is over, you can always perform transient analysis and DC analysis also for this experiment. In the DC analysis, you will observe that there will be no phase shift between input and output. Means when input increases, output also increases. And in the transient analysis, you will again see that input and output will be the same phase. Transient analysis performed basically to verify the shape of the output waveform such that we get the undistorted waveform. That screenshot is not shown here in the manual. So after the simulation, we can proceed for the layout of this common drain amplifier. You can see here, let me slightly zoom out. Now you can see the layout. I hope it is clearly visible. Now, for this experiment, we have tried the horizontal approach instead of the vertical approach. In the sense, the upper transistor is having a 50 micrometer width, that is the amplifier transistor. The lower transistor is the resistive transistor, which is having only 10 micrometer width. Now you can see in the upper transistor, we have connected wires at the top with the metal line. Now both NMOS FETs are in P substrate. So around the transistor itself, the black screen itself is the substrate. Now the body of the NMOS FET is the substrate itself. Substrate needs to be connected to VSS because both are now NMOS FETs. And every 10 micrometer, we should place one wire so as to avoid the leakage charges or the leakage current. So you can see there, I will zoom in. Now you can see every 10 micron, there is this wire connected and all those wires are finally connected to the VSS track at the right side. And to the gate of the upper transistor, input is connected. You can see this wire here. And for the lower transistor, this is the V bias. Now, the source of the lower transistor is connected to VSS. This is the source. Upper one is the drain. Now, the drain of the upper NMOS is connected to the source of the, drain of the lower NMOS is connected to the source of the upper NMOS. And the drain of the upper NMOS is connected to VDD. This can be seen here. So, upper one is drain here, lower one is source here. Similarly, here, even in the case of lower NMOS FET, upper one is drain, lower one is source. And the body of the lower transistor is also connected to VSS by means of these two wires. Every 10 micron, we should have wires. That is why we have these two wires. So, this is the complete layout of the common drain amplifier. Now, with this, I am coming to the end of today's experiment. If students have any questions, you can ask me, or else we will conclude today's class. Deepak has already put attendance link in the WhatsApp. I think Deepak has put Deepak created the assignment also for today's observation books upload. Deepak, have you done it? Deepak is trying to speak. Deepak? You can put it in the chat box also if it is there. If you are unable to speak, there may be some audio issue. Okay, I hope Deepak has created that assignment for the PDF upload. Students can remain in the meeting. The meeting will be on. You can write today's observation book and you can upload it into Google Class. Yeah, Deepak has put the answer in the chat box that he has done it. So I will stop recording and I will remain muted also. I will stop sharing the screen also. But the meeting will be on as and when students
Sir, I have
submit.
a
Yeah.
non-academic doubt.
Yeah, tell me.
Sir, today should be holiday, no, sir? Das Jayanti in Karnataka.
In autonomous structure, we don't have the holiday. In autonomous structure, we can define our own holidays. So,
So, but
yes,
will it be compensated on this Saturday? Will be this Saturday.
not probably, because it is not defined as a holiday. The reason is, in a year, there are only a limited number of holidays as per the university. Now, university gives one relaxation to autonomous institution. They can define some of their holidays as normal holidays or restricted holidays. That way, the list of holidays is released by university only. Now, university will say these many fixed holidays, these many flexible holidays. Out of the flexible holidays, each institution can choose some number as holidays, but the total number of holidays in a year is fixed. For example, in 2020, university gives a calendar of events where, let us say, the total number of holidays should not exceed 20. Imagine, I'm just giving a rough number. Now, in that 20, we have the option to choose some of those restricted holidays as regular holidays. So that way, VTU has a different list of holidays. Autonomous institution can have their own list of holidays. Now, when we define holidays for some other event, VTU may not declare holiday for their affiliated institutions, but the total number of holidays for the year remains the same. That way, today we don't have holiday. Okay.
Okay, sir.
Fine, fine. Okay, I'll stop sharing the screen and I'll remain muted. If students have anything, you can always put it in the chat box.